Hello everyone. We are here to talk about spatial databases today, and we are group 3 consisting of Harsh, Yash, Ishita, and Sindhuja. Before we dive deep into spatial databases, we first wanted to talk about a couple of examples of what spatial data actually represents. So if you look at the three images on this slide, in the first you see a road network which basically represents a bunch of roads in Tallahassee and shows the intersection between them, highlights a couple of important roads and labels them. In the second one you see a satellite image which is taken from above the ground, representing the positioning of houses in a specific area, where they're located, what the region might be, etc. And the third one represents a VLSI layout. So basically what we're looking at in spatial databases is some sort of area or location or position and seeing what variables are of importance to us in that. So what exactly is a spatial database now that we know what it represents? A spatial database system is also a database system and basically can be defined as a DBMS with additional capabilities for handling spatial data. So the spatial database offers spatial data types, also called as SDTs in its data model and query language. And these are basically structures in space. For example, a point, a line, or a region. And the spatial database also defines relationships among these. So if a point were to intersect with another line, this would be represented as a relationship in the spatial database. Now, the spatial database also supports SDT in its implementation, providing two major features. The first being what we call as the spatial indexing, which retrieves objects in particular areas without scanning the entire space, so this does not waste any memory. And the second one being providing efficient algorithms for spatial joins and not just simply filtering the Cartesian product. So we look at what is a GIS, or a Geographic Information System, and we see that the GIS combines spatial data from many sources to share them with different people. For example, a use case might be something of the sort. A city might have a wastewater division, land records, transportation, and fire departments, and these could be connected using a geographic information system from common spatial databases. So what is an attribute table in GIS? Similar to how you have tables in DBMS, an attribute table consists of spatial features which store where objects are located on a map. A non-spatial attribute table explains what the objects on the map represent. These are very similar to spreadsheets. A field name should be descriptive of the information being entered in the column, which is basically the name of the column. For example, the average population might have a field name of average_pop. Rows in an attribute table represent a spatial feature in the dataset or an associated record of that dataset. So similar to the DBMS, rows in an attribute can have relationships with the spatial features. And there are three types of major relationships: the one-to-one, the one-to-many, and the many-to-many relationship. So we look at an example of a one-to-many relationship. If you were to look at the map on the top left of the screen, we see that there are 2 points on the map, A101 and A102, both which represent mountains. The first table that you see here stores details of the latitude, the longitude, the name of the mountain, and what kind of object it is, which is the mountain, and has an ID associated with it. And the second table shows observations of animals at the site and also contains details of which year that observation was made in. It is also connected with a survey ID, which is similar to the ID, which is the same as, which is connected to the ID in the first table. So what is the purpose of using something of this sort? It reduces redundancy by not having to store details like the latitude and longitude again, even though those are variables of importance in this table. So we look at what modeling objects in spatial databases are, and as we talked about before, We first have what we call a point. So a point is an object represented by only its location in space. For example, a center of a state. The second is a line, which is actually a curve or what we call a ploy line, which is representation of moving through the connections in space. So it could be a road which is connecting two points or a river connecting two points. A region is a representation of an extent in 2D space. For example, a lake or a city which covers a lot of points. A partition is a set of region objects that are required to be disjoint, adjacency or region objects with common boundaries. For example, thematic maps. Networks are embedded graph in plane consisting of set of points, vertices, and lines or edges, objects. Example, highways or power supply lines or rivers. So we first look at querying in a spatial database, and we are looking at spatial selection within this query. So spatial selection basically returns those objects satisfying a special predicate within the query object. For example, if you wanted to query something of this sort, all cities in Bavaria, you would write a query wherein you would select the name from the table where there's a specific condition. Similarly, if you want to select all the rivers intersecting a query window, you would select all the information that you needed from the table, again on a condition. In the third one, we have multiple conditions where we're selecting a name of a city from the city table where the distance from Hagen is less than 100 kilometers and the population is greater than 500k. Next, we would be looking at spatial joins, which is also a part of querying. So what a spatial join does is it compares any two joined objects based on a predicate on their spatial attribute values. For example, if you wanted to obtain for each river that passes through Bavaria, all the cities within less than 50 kilometers, you would select the attributes that you wanted and you would use the two table names from which you wanted this information, and you would put a condition which would tell you that the attribute from one table intersecting with another table, and put the condition where the distance is less than 50. There's an important concept in spatial databases called spatial indexing, which is basically used to expedite spatial selection or even spatial joins. It organizes space and the objects in it in such a way that only some parts of the objects need to be considered to answer a query. So there are two main approaches we use in spatial indexing. One being a dedicated spatial data structure. So we use what is called an R tree in the spatial indexing space. And we also have what we call a B tree, which is used when spatial objects map to a 1D space are needed to utilize standard indexing techniques. Next, we look at memory organization in spatial indexing. So a spatial index structure basically organizes the points into buckets. So each bucket has an associated bucket region, which is basically a part of the space containing all objects stored in that bucket. So for point data structures, the regions are disjoint and partition space so that each point belongs to precisely one bucket. And for rectangle data structures, bucket regions may overlap. So if you look at the image on the bottom of the page, you will see what is called a KD tree partitioning of 2D space, where each bucket can hold up to 3 points. So if you notice, there is no partition or bucket that has more than 3 points. Lastly, we look at the system architecture, which talks about how a spatial database is very similar to a normal DBMS that we see. And the only clean way to accommodate these extensions of the spatial database is an integrated architecture based on the use of an extensible DBMS. So there's no difference in principle between the following points that we see here. So if you were to look at a standard data type such as a string and a spatial data type such as a region, there would be no difference. The operations are the same too. In fact, concatenating two strings or forming an intersection of two regions would be more or less the same thing. Clustering and secondary index for standard attributes, example a B tree, and for spatial attributes like an R tree would be similar. It would also be similar to use a sort or merge join and bounding box join in spatial databases. Query optimization is only reflected in the cost functions. So overall, we have covered what spatial databases consist of. There are some complex querying procedures that can be done in spatial databases, but just as an overview, we kind of covered indexing, selection, and joins in spatial databases. Thank you.